The next thing we're going to talk about in Chapter 5 is a perpendicular bisector. We're still dealing with triangles. In fact, if we look over here at these diagrams, we have a triangle with a line going through it. That line is a perpendicular bisector. And a perpendicular bisector is a segment, a ray, a line, or a plane that is perpendicular to a segment at its midpoint. Now, the word perpendicular bisector, actually the words perpendicular bisector, are very, very important. In order for something to be a perpendicular bisector, it must satisfy two criteria. It must be perpendicular and it must bisect a segment. If you don't see both of those marks or be able to prove both of those, then something cannot be considered a perpendicular bisector. A little side note, when something has to satisfy two criteria, remember it is called a biconditional statement. Biconditional meaning two conditions that it must satisfy. The first thing that a perpendicular bisector does, in a plane, if a point is on a perpendicular bisector, then it is equidistant from the endpoints. Here we have perpendicular bisector CP. We can see that it is perpendicular and that it bisects. And because point C, right here, is on the perpendicular bisector, then C is the same distance from A and from B. So we could say that CA and CB are the same length. Now, there's a reason for that. If we look at this diagram really, really closely, this is just considered the proof, by the way. This is just explaining why CA and CB are the same. There's a lot of things in math that you just have to take for granted. You have to take for granted that 1 plus 1 equals 2. But there are certain things that we can explain. For example, I want you to look at this triangle and this triangle. Now, there are things about these two triangles that we see right away. One thing we see is that AP and BP are the same length, so they're congruent. We also see that both of these angles, sorry about that, we also see that both of these angles are congruent, or are 90 degrees, which means that they're congruent. There's one more thing. CP is in both triangles. When you say that CP is in both triangles, you can set them congruent to each other. And remember, that's the reflexive property. When you say that CP is congruent to CP, that both triangles have 90-degree angles, and that both triangles are congruent on this side, you have a side-angle-side congruency. So that this triangle, right here, and this triangle are congruent. The triangles are congruent. And if the two triangles are congruent, then this part and this part, because they're corresponding parts, have to be the same, or they have to be equal. Now, if we drop down into the next theorem, we see the same picture, but the triangle has been flipped over. Now, up here, the whole premise, or the whole reason that we have this theorem, is to show you that if point C is on the perpendicular bisector, then it is equidistant from the two endpoints. The opposite of that theorem, or the converse of that theorem, is to say if you have a point equidistant. Up here, we have a perpendicular bisector. And because we have a perpendicular bisector, we have a point that is equidistant from the endpoints. Here, we're told a point is equidistant from the endpoints. Therefore, it lies on the perpendicular bisector. Remember, the word converse is taking an if-then statement and flipping it around so that it's a then-if statement. Up here, we're proving that two segments are congruent. Oh, that was horrible. We're proving the two segments are congruent because they both lie on the perpendicular bisector. Here, we're telling you they're congruent. Therefore, it lies on the perpendicular bisector. This is a whole lot of wordage and math for a very, very simple concept. Once we start actually solving problems like these, you're going to realize, wow, these are very, very simple. Or at least I hope you will. Let's actually go ahead and just jump right into it. In example 1, we're told to determine whether BD, in fact, let's highlight BD just so everybody's on the same page, whether BD is the perpendicular bisector of AC. If it is, solve for X. The first thing I see in this problem over here is that this distance and this distance are the same. 8 and 8 are congruent. Well, if these two distances are the same, then D has to be on the perpendicular bisector. And the reason for that is this. If your point is equidistant from the endpoints, then it lies on the perpendicular bisector. Here we have a point, D, and it is equidistant from the endpoints. It's 8 distance from C, and it's 8 distance from A. And simply because of that, it has to be on the perpendicular bisector. Now, over here, we don't know that it is for sure because we don't have a perpendicular mark. We don't have congruency symbols, so we don't know that it is on the perpendicular bisector. But if we can prove that this distance and this distance are the same, then we can solve, or then we can prove that D is on the perpendicular bisector. Now over here we were told that they were the same. They're both 8. Over here we're going to have to solve it to prove it. If DC equals DA, then D is on the perpendicular bisector. There's our geometry statement that we need to prove. Now we're going to substitute in what DA and DC equal. DA is 5x. DC is 3x plus 14. And now we're going to solve this because if we can find a value for x, we can say that D is on the perpendicular bisector if x equals this. So we can solve this problem using our algebra. What I want to do is get all my x values on the same side. Now I'm going to move 3x to the other side. How do you move a positive 3x? Or how do you cancel it out? You subtract 3x from both sides. When you do that, you get 14 equals 5x minus 3x is 2x. I don't know why that's acting up. Excuse me. Little hourglass telling us that we have to stop for a second. There we go. Now I have the problem 14 equals 2x. How do I solve for x? I divide both sides by 2. And when I do that, I get x equals 14 divided by 2, which is 7. And because x equals 7 on both sides, we get this side to equal 35, this side to equal 35. Both sides are equal, just like over here. And so D must be on the perpendicular bisector. Try and prove that D, or whatever this point is the same distance from the endpoints. And if you can prove that, then you've proven that it's on the perpendicular bisector. Now, if we have a triangle, like this, you're seeing one perpendicular bisector, okay, where it's perpendicular and it bisects. But couldn't we draw a couple more? Couldn't this have a perpendicular bisector and this have a perpendicular bisector? So now we're going to be talking about all three. And when you get all three perpendicular bisectors, that's called the concurrency. That's where all three meet. You can even see this little diagram. That this line is the perpendicular bisector of this segment. This line is the perpendicular bisector of this segment. And this line, as small as it is the perpendicular bisector of that segment. Now, let's read the theorem, or the concurrency of perpendicular bisectors. The perpendicular bisectors of a triangle intersect at a point that is equidistant. That's very, very important. Muy importante. Come on, change color. You can do it. Good boy. Equidistant from the vertices. Now, vertices is a fancy word for the corners of a triangle. All three of these perpendicular bisectors, you can see, meet at this point. They labeled it P. And because all three meet at P, we have something very special. P is the same distance from A as it is from B and as it is from C. All three of these lines are the same distance. Now, you might say, well, why are we doing this? Let me show you. In geometry, there are times, let me get rid of this, excuse me. There are times when you need something rotated. For example, if I draw a triangle, and I need this triangle to rotate clockwise, there's a specific point in here that I'm going to rotate it on. And that point happens to be the concurrency of the perpendicular bisectors. Let me show you something. I'm going to get out my handy dandy compass. And I'm going to put the center of my compass right on that point P. And what I want you to see is that this point represents the center of a circle. That point, at that point, I could rotate A, I could rotate B, and I could rotate C in any direction I want, as much as I want. But that point, if I needed to rotate this triangle, that is the point that I would want to rotate it around. And that's why we find this spot, or this point. It's not the center of the triangle. It doesn't represent the part on the triangle that would be the strongest structurally, but it is the point at which, if we wanted to rotate this triangle, let's say you wanted to rotate it 90 degrees, so that A is up here, B is over here, and C would be like over here. That is the point at which you would want to rotate it. And that's the concurrency of the perpendicular bisectors. It's where the perpendicular bisectors of every side meet. Now, in example 2, let's just get this guy out of here. We're shown a county fair. Okay, I went to the fair this summer. It was a lot of fun. I took my daughter to see the horse barns. She loves horses. I love horses. It was a lot of fun. In example 2, you are in the center of the fairgrounds. Okay, let's just say, for sake of argument, these are the gates. And you drove through the gates. You're looking for the closest bathroom. Who doesn't like a good bathroom, especially on a fairground? Usually they smell awesome and are perfectly taken care of. If you've ever been to the fair and you have had to use the bathroom, you know I'm totally joking. According to the diagram, which of the 3 bathrooms would be the closest? Would it be E, F, or G? You're in the center. In the center of that circle is D. Now, how do we know it's in the center? Because this distance, and this distance are all the same. Although they might not look it, they are the same. So now we need to figure out which one of these is closest. Well, I could very easily just get a ruler out. Let me find my ruler. Bingo. Ruler. Put it on 0. Rotate it, and A is just over 55 millimeters away. Or it's just over 5.5 centimeters. Well, I can do the same thing and find out how far B is. And B is 83 millimeters, or 8.3 centimeters. and C is 85. So, excuse me, I'm sorry, we're supposed to be measuring the bathrooms. This bathroom, we'll call it G, is about 40 away. This guy's about 45. And again, these are millimeters. And this guy's 28. We can see that F is the closest bathroom that you want to go to. Not necessarily the cleanest, but it is the closest. This distance is the shortest of those three perpendicular bisectors. We can see, as soon as we get rid of our ruler, that each one of these, GD, ED, FD, are all perpendicular bisectors. They're all perpendicular to their line segments, and they bisect them all. And again, these distances, because D is in the center, all three of these distances to the corners are the same. We can use that information to actually solve it. The point of intersection of the lines, the point of intersection of those three, is called the point of concurrency. Sometimes this point changes positions depending on what type of triangle you have. Here, we have an acute triangle. And we can see that the intersection of all three perpendicular bisectors is inside the triangle. Here we have a right triangle. And we can see that the intersection of all three perpendicular bisectors is on the triangle and on the hypotenuse. More importantly, it's on the triangle. It's actually on one of the sides. Here we have an obtuse triangle. And we can see that that point of the three perpendicular bisectors is outside the triangle. And again, you'll notice that the concurrency is the center of all three circles. Okay, a lot like what I showed you back here. Okay, but depending on what type of triangle you have, will determine where it's at. Maybe it's inside, on, or outside the circle. Note, what do you notice about the radius of the circles? Meaning, what do you notice about the distance from one of the edges to the center? Okay. And you should notice that they're all the same. What do you notice about the perpendicular bisectors? Well, first of all, not only are they perpendicular and they bisect, but they intersect at that center. Now, when you can take a circle and draw it around your shape on that point, that is called a circumscribed circle. At some point during the year, actually coming up pretty soon, we're going to talk about another type of circle that occurs on the inside of the shape. And that is actually called an inscribed circle. Not yet, but just kind of giving you a heads up of what's to come. But just to understand something, that point of concurrency for the perpendicular bisectors always is the center of that circumscribed circle. Oh, that was horrible. The circle that goes on the outside of our shape, regardless of what kind of triangle it is, that concurrency point of the perpendicular bisectors is always the center of our circle. In fact, we even call it if it's a circumscribed circle, that point is called the circumcenter. And you'll notice it's P on all of these. Okay, and that's just a little note. Okay, again, this is also the point of rotation. If you wanted to rotate any of these points, you would do it around that circumcenter. you'll notice how the edges of all the triangles are always on the sides of the circle, which allows you to rotate them. And this is dealing more in engineering. Let's say you have a part that you need to spin. Maybe it's a rotor, maybe it's a blade. Okay? There's a point of rotation where no matter what, those parts stay the same distance apart. And that point is what you're looking for. So maybe sometimes you might have to draw a triangle and find that point. Other times, maybe somebody already measured it and said, hey, that point is right here. But this deals more with engineering. Let's take a look. We're told to find the length of AD. Here's AD. Now they give me some other information here. They give me that DG is a perpendicular. There's my perpendicular mark. And it's a bisector, so it's a perpendicular bisector. They tell me that DF is perpendicular and bisects, and that DE is perpendicular and it bisects. Well, if all three of those perpendicular bisectors meet at D, what does that tell me about AD, CD, and BD? What does it tell me? Let's go ahead and look. The concurrency of the perpendicular bisectors is equidistant from the vertices of the triangle, or equidistant from the corners. So the length AD, CD, and BD are all equal because they're equidistant. Okay? If we break down equidistant, we get equa for equal. Distant, meaning distance. So they're equal distance apart, meaning they're all the same. Well, I can see that they gave me CD. They told me it was 7. If CD is 7, what does that tell? Not 7D. Wow, way to go. If CD is 7, what does that tell you about BD? And what does that tell you about AD? It should tell you that they're both 7 too. Because all three of these points are the same distance apart. Let me show you. I'm going to get my compass out. I'm going to find the distance as best I can. I'm going to not that far. I'm going to find the distance of CD. There it is. That's the distance right here. That's the distance of CD. It doesn't change. There it is. Now, if I rotate this, I should hit A. Oh, look at that. AD is the same length. And if I keep going, well, my drawing is a little bit off. B should be way up here. But B and A should be the same length. And that's my fault. My drawing is horrible. Bad drawing. Not a good drawing. Let's move B up here. Oh, look. B is the same length. See how everything works out well, especially when you're the teacher. If CD is 7, then AD is 7. BD is 7, and we've answered our question. Let's look down here. We're told to find the length of BF. There's BF. Now what I want you to notice is this. That this ray, CE, is perpendicular and bisects BD. And if CE is perpendicular and bisects, what does that make it? Makes it a perpendicular bisector. And we learned that if a point lies on a perpendicular bisector, whoops, too far. We can get rid of this guy, he's in the way. If a point lies on a perpendicular bisector, then it is equidistant from the endpoints. In this drawing, C is on the perpendicular bisector, so it's equidistant from A and B. If we take that and apply it to what we know, if F is on the perpendicular bisector, which is right here, then BF and DF should be the same length. Now, I can see that CE continues on. Okay? It's a ray or a line. It goes on forever. So it should intersect F, right? But we can't prove that. We have to prove it. I have to be able to say if F is on the perpendicular bisector, or if it lies on CE, then this length and this length are the same. That's why I wrote this geometric statement right here. Now I'm going to substitute in those values and find out if I'm going to find out if these two sides are the same. Well, BF is 6x minus 5. I'm a little bit off, apologize. 6x minus 5. And it should equal DF, which is 4x plus 1. Now I need to try and solve this and say if x equals something, then BF equals DF. So I need to solve this using my algebra. The way I do that is by getting all my x's on the same side. So I'm going to move 4x to the other side. The way I move a positive 4x is by subtracting it. When I do that, they cancel out on this side, and I get 6x minus 4x, which is 2x, and I drop down everything else that I didn't use. Now I need to move this negative 5. The way you move a negative 5 is by adding. When we do that, we get 2x by itself. 1 plus 5 is 6. So now I have an easy, simple, one-step problem to solve. 2 times x equals 6. I need to find out what x equals, so I'm going to divide both sides by 2. That will cause this problem to undo itself, and the 2's will cancel out. And I'm left with x equals 6 divided by 2, which hopefully you can simplify to 3. I found out that if x equals 3, then this segment and this segment are the same. Now, it would be great if I was done because I found x. Remember something. You just solved an algebra problem. You didn't answer the geometry problem. The geometry problem is asking for the length of BF. BF equals 6x minus 5. Well, I need to find out what that is. So I'm going to substitute in my x, which is 3. So instead of saying 6x minus 5, I'm writing 6 times 3 minus 5. And now I can simplify that. 6 times 3, is 18. 18 minus 5 is 13. So BF equals 13. There, we set our two sides equal to each other to prove that F was on the perpendicular bisector. If F is on the perpendicular bisector, then these two sides should be equal. We set them equal and solve for x. We found out x was 3. Then, to answer our original problem and find the length of BF, we plugged in or substituted 3 for x. Then we simplified and found out that BF was 13. So let's review, because there's a lot going on. We learned about perpendicular bisectors. We also learned about their point of concurrency, or where they meet. We learned that where they meet is equidistant from the three vertices, or from the three corners. Perpendicular bisectors, concurrency of perpendicular bisectors, and how they're equidistant from the three vertices, or the three corners. You're going to take what you learned and apply it in your homework tonight. Let's take a look.